In this video, I'd like to talk about the difference between an object's total distance traveled and its displacement. I have an object that's moving in a straight line, and this graph gives its velocity. So it speeds up and then it slows down, and right here the velocity is 0 and then the velocity is negative. And what this tells me is that on some coordinate axis, I have an object that travels to the right, or I could think about it up, or whatever the positive direction is, but I'm going to think about it moving to the right. It speeds up, and then it slows down and stops, and then when the velocity is negative, I know it has to turn around and go back the other direction. And going in the negative direction, the speed is increasing, and then the speed is decreasing. And what I'm really thinking about here is an object that is going to the right for a while and then doing exactly the same thing to the left. If I look at my velocity graph, these two peaks match each other, just flipped upside down. I think what I have here is an object that travels to the right for some period of time, for 2 seconds or 2 minutes or whatever the units are, and then turns around and gets back to where it started. And so right there, I have this idea of I did travel some distance, but I got back where I started. Total distance traveled is talking about literally how far I went to the right and then added to how far I went to the left. So if I walk 3 feet to the right and 3 feet back to the left, I've got a total of 6 feet, and that's my total distance traveled. But when I say displacement, I'm talking about just my net gain. So if I walk 3 feet to the right and 3 feet to the left, my displacement is 0. I got back right where I started. If I had gone 3 feet to the right and then I walked back only 2 feet to the left, then my displacement would be that 1 foot difference. And that's really the difference. Total distance traveled is always talking about literally how far. In our previous video, to talk about that, instead of looking at velocity, we talked about maybe looking at speed. So I take an absolute value, everything would be positive, and then I could calculate the total distance traveled. For displacement, I literally will just use the velocity graph. Now, for total distance traveled, our approach was to think about the graph of speed, which is the same graph, just with this bit flipped over, because the negative values become positive when I find the absolute value. Speed is the absolute value of velocity. And then if I take the approach from the previous video to approximate the actual total distance traveled, I divide my x-axis into some number of sub-intervals, and I'd form rectangles, and maybe I find an upper sum, and that would give me an approximation, because what I'm looking for is the area under the curve to find this, and somehow my rectangles have gotten off, and then I'd have to calculate the area of those rectangles, add them together, and the idea would be if I use more rectangles, I get a better answer. But on this example, I can actually do something even more simple. Those rectangles are trying to approximate an area under a curve, and well, if I really look at the shape this graph is making, I don't think I really have to approximate its area, because when I really look at it, the area under this curve is just 2 triangles, and I can just calculate those areas, right? The area of a triangle is 1/2 base times height. Well, the base of this triangle is 2 units. The height of that triangle is 1 unit, all right? So that is 1 square unit of area, and this identical triangle is also 1. So I think the total distance traveled is 2. Now this is really starting to bother me that I didn't assign units, so I'm just going to come up here to my original graph that was given and say that time was in seconds and that velocity was in meters per second. And that's 2 meters then. I've traveled a total distance of 2 meters. And so now let's talk about the velocity graph and how to use that to figure out the displacement. Well, if I think about my rectangles here, right, even if I wanted that upper sum, what I'd have is some rectangles would be facing downwards. I'm not doing a very good job of keeping a consistent width here, but that's okay, we get the idea. Well, if I remember how to format finding that area, it was always the function evaluated in x times the width of the rectangle, which here would be a change in time. And then I just do that a whole bunch for all of the subintervals. And what I realize here is that sometimes the velocity is positive, but for the second half, the velocities are negative. So some of these calculations are negative. Literally, the rectangles that face up, the calculation would give me a positive value, but the rectangles that face downwards, I would get a negative value because I'm going the other direction, right? That area is supposed to be talking about a position. So I'm either moving to the right or moving to the left. And so what would happen is I have one positive area and one negative area. And what I see here is that these are the same two triangles. One's going to be a positive one, and one says I was moving the other direction. So I have a positive one, minus one, and I get 0. So the displacement is 0. Because I moved to the right 1 meter, and then I moved back to the left 1 meter. All right, that's the difference between displacement and total distance traveled. For total distance traveled, we're looking at speed. For displacement, we actually get a net area. Any bit above the graph is positive because that would be moving to the right, and any bit below the x-axis would be negative because that's moving to the right.